When preparing your work for production, it's important to ensure that your ideas, methods, and models will scale up both in terms of the number of times your work needs to be evaluated and run, and also as the size of your dataset grows. When your methods get put into production, the code that you use to evaluate them gets used more often, and it's going to get used on more data as well. If this doesn't involve someone translating your code into a more efficient language, you need to ensure that your current implementation is going to be up to those standards. There's two main aspects that we need to consider here. The first is scalability in terms of computation time, and the second is scalability in terms of the memory requirements of your code. When we're doing this, we need to balance a trade-off between the amount of time and effort that we're putting into developing this new version of our software and the usage costs that would be associated with running the code in a potentially suboptimal but slightly improved manner. So as an example or thought experiment around this idea, let's consider performing some Bayesian inference, where we have an intractable model, so we have to use Markov chain Monte Carlo methods to obtain approximate posterior samples. We do this by setting up a Markov chain that in its stationary distribution would give us samples that well approximate the posterior distribution that we're interested in modelling. The problem here is that this sampling process can take quite some time, and the chains can be quite dependent, so you need to make very many dependent draws to be equivalent to only a few independent samples from this approximate posterior distribution. What this means is that it can often take quite a long time to evaluate a large enough collection of samples, and we've got a solution to this, but it takes about a day to get enough samples from this distribution. If we then try and optimize that code, we might be able to identify and amend some bottlenecks that are slowing us down, and if we fix those, reduce our overall evaluation time to about 24 minutes instead of 24 hours. But what we need to ask ourselves, is this 60 times speed up actually any better? And that's going to be very context dependent. Firstly, we need to think about whether the number of human hours that have gone into improving this code offset the improvements in runtime. And this is related to how frequently this code will be used. Yes, we've sped things up massively by a factor of 60, but if we're only going to run this code 3 or 4 times, and it's taken us several weeks to make these improvements, then that isn't going to be a justifiable trade-off. However, if we're putting this code out into the world for other people to run as well, and it might get run many hundreds or thousands of times, then this sort of speed up is worth the time that you've invested. Another aspect to consider here is whether the changes that we've made in achieving this speed up leave our code as safe, as stable, as general, and as readable as before. Usually you have to trade off at least one of these for your code to scale well to larger numbers of samples. You might speed up each individual sampling by removing some of the checks and thus making the MCMC scheme slightly less safe or less stable, or you might have to use more specific versions of functions that are really tailored to a particular task, making the overall code less general. An alternative approach is to use different programming strategies that more directly address the problem that you're trying to solve, but do so at the cost of making your code more difficult to read. An example of this might be implementing the same algorithm, but in a lower level programming language. One thing to be aware of is that trying to optimize your code can actually, in the grand scheme of things, be worse than doing nothing at all. The reason for this is that if you try and optimize everything as you go along, you can spend a lot of energy trying to make very minor gains in areas of your code that in the end aren't going to be particularly cumbersome. There's 2 aspects to this. The first is trying to optimize in the wrong parts of your code, and the second is trying to optimize at the wrong time in your development process. If we're trying to optimize everything in a linear manner as we're writing, then we don't know which parts of the code are actually going to be the most important, where we can make the biggest change to the efficiency of our code with the least possible effort. The timing of that evaluation as well is very important. What is causing a bottleneck at the start of a project might not be the same thing that's causing a bottleneck at the end of a project. So for example, if we return to that MCMC scenario, at the start of your project, it might be that reading in your dataset is what's causing your code to be the slowest. But as you scale up the number of samples that you're doing, then this becomes negligible in comparison to the costs for sampling from the approximate posterior or storing those sampled values. This is why when we're doing this sort of optimization and testing, we want to be as close as possible to the true production scenario. Here on the right hand side, we've got a plot that shows this sort of trade-off between the amount of time you have to invest in coding up improvements and the amount of computing time that remains after those improvements are made. We can see in orange that we've got a Pareto frontier where there are 3 solutions that are clearly better than the other ones, but it's a subjective choice as to which one of these is actually the best in any particular scenario. We might prefer the version that doesn't do quite so well as the other 2, but doesn't take us very long to get there. Or if this is a really important bit of code that gets run many millions of times, then it might be worth that additional coding time to get the computing time to drop by another 50%. So in this video, we're going to have a look at how to identify where those bottlenecks are within our code, and have a look at some really quite simple methods that we can use to try and alleviate those. These will mainly be strategies for writing scalable R code, but there will be a little bit of transferable knowledge to other languages, and also linking in the connection between R and other languages. So the most basic way that you can profile your code is to use R as a stopwatch and literally measure how long it takes to run. You can do this using the systime function that is built in with base R. And here we've just got an example where we put the system to sleep for half a second, where we start a stopwatch just before that and take the time just after it's finished. This is a nice accessible way to start profiling your code. If you want to add in some more fancy features, for example timing different sections of your code all in the same run, then you can do that using the TikTok library. Here we do exactly the same thing in the left-hand side example, where we start our timer using tick, stop the timer using tock, and we get some nice printed output telling us how long our code is run for. By nesting these tick and tock function calls, we can get more complex breakdowns of how our code is performing. So here we have an initial easy part of the code that we're timing, a second harder part of the code that takes a full 3 seconds to run, and then we're also evaluating the overall time it takes to run our code. So this sort of basic timing is good in understanding which parts of your code are the fastest and slowest, but it doesn't really help you diagnose which functions within your code it is that are taking up all of the time. One way that we can establish this is to keep stopping the code very briefly at lots of small time intervals and examine the call stack at each of those time intervals. The call stack is a description of what the current function that's being evaluated is, as well as the function that called that function, and the function that called that function, and so on, all the way up to the first top-level function that you called. So you can see here the parallels with functional programming, where we have nested function calls, and here we're evaluating at each time point which function we're running, and the functions that have led us to run that function in the first place. If we do this at very many time points, then we'll know which function we're running at almost any time during our code's evaluation, and we can use that to measure, or more accurately to estimate, the proportion of working memory that's being used at any given moment, and also the total time that is spent evaluating each of our function calls. We'll start off with a toy example, where we have 3 different functions that are called in a nested manner. We've got a function h that just pauses for a second, a function g which pauses for a second and then calls the function h, and a function f, which pauses for a second, runs the function g, then pauses for another second and runs the function h. What we can see on the right hand side here is a visualization of the call stack for that function. So to begin with, we're running the function f, which is calling the pause function. So here we have f at the bottom, and stacked on top of that, we have one pause function. One time unit in, we then have the function g being called from within the function f, which then causes the pause function from within the function g. So we have three functions stacked here. After that brief pause, the function h gets called from within the function g, and then within the function h, the pause function is called again. So here we have four functions in the call stack at time 2.5, for example. At the top of the stack, we've got pause, then h, then g, then f. We can use this sort of visualization to see within f which of our sub-functions we're spending the most time in, and where we might want to focus our efforts in terms of optimizing our code to improve the overall performance of f, either in terms of memory allocation or in terms of computational time. We can make this same sort of visualization for our actual code using some functions from the profviz package, and indeed the function itself is called profviz as well. So here, by saving our set of functions into a separate script, we get a nice visualization of how long we spend on each line of the script, and an interactive graphic of the same form that we just saw that lets us explore how long we're spending within each sub-function. Here we can see that we spend a lot longer in the h function than we do in the function g, but this is because the function h is called more times overall. The bar plot at the top here is showing us the amount of time that we spend within each function overall, not how long it takes one evaluation of this function to run. So there's a couple of things to note when you're time profiling your code. The first is that there's going to be some slight stochasticity in with this. You're going to get different results every time you run the function, because exactly how long things take to run is going to depend on the internal state of your computer, and that's going to change over time as it's processing other activities in the background as well. Usually this really isn't a very big deal because it mainly affects the fastest parts of your code, so those functions that take the shortest time to run. These aren't the parts that we're really interested in when we're profiling our code. We want to find parts that take the longest, that are the slowest, and try and improve those. One thing that you should be aware of though is that in data science we're often using stochastic simulations or stochastic methods, and we want to isolate that stochastic variability from our evaluation of how fast our code is. So as an example of this, if we have a data set that changes size between each stochastic run, then that isn't going to be a fair comparison between two runs of this function, one with the original code and one with the new and improved code. What we need to do is set our random seed to make sure that our comparison is fair over those different runs. A second thing to be aware of when trying to profile your code is that this will only go down as far as non-compiled functions. This is a distinction between two different ways that R can load a function. In our first example, like our pad with NAs function, it can be stored as literal R code. This is then evaluated as it's needed. But the other way a function can be stored is as a compiled function, and this is the case with lots of the base methods. These functions are written not in R itself, but directly into a lower level programming language like C. This means that these functions are pre-compiled, and so we can't access the script that is used to run them. This means that the profiler also can't access that script, and so we can't get any lower level detail using the standard profiler from profviz about what's happening in this internal C code. If you do ever need to do this, if you really need to optimize some compiled code, then you might be interested in investigating the joint-prof package to do so. So as well as profiling the speed of your code, the amount of time it takes to evaluate, profviz can also measure the memory usage of your code, which we deliberately avoided in the previous example. So in this second example, what we're doing is starting off with an empty integer vector, and for a sequence of values from 1 to 10,000, we're going and appending that number onto the end of our integer vector. So we first have a vector of length 0, then 1, then 2, all the way up to 9,999. What we can see here is that our memory usage has both a large positive and negative component, and that's because lots of objects are being created and deleted as part of this code. This might seem unusual to you, but it's a particular feature of R that is known as copy on modify behavior. So whenever an object in R gets modified, it gets relocated to a different address in your computer's memory. This means that this sort of iterative extension of objects and moving information around within your computer. We can see that evidenced here by the GC function taking up most of the time within our function call. This GC stands for garbage collector, and this is what is clearing up your memory usage as your vector gets moved around your computer's memory. This sort of inefficiency is exactly why in all of the previous code examples we've been pre-allocating storage for our outputs of our functions wherever that's possible. In some cases it's not going to be possible because you don't know the size of your output before the code runs. There are some interesting strategies and data structures that can get you around that problem, and if you'd like to learn some more about those, I'd recommend you have a look at either the R Inferno book or the Efficient R book. So once we've identified which parts of our code are bottlenecks in terms of either storage or timing, what can we actually do to try and improve our situation? The first and most widely made recommendation is to vectorize your code. R is a heavily vectorized language where functions can take vector-valued arguments. As an example, consider taking two sequences of numbers and trying to find the element-wise product of those. If you're writing this in Python, C, or some similar language, then your immediate approach to this might be to iterate in a for loop through all of the elements of those vectors, multiplying them together and storing them in a new vector called z. But in R, this approach is by far inferior to directly multiplying those two vectors together. This is because the direct multiplication extracts that for loop from R, in which it is relatively slow, into C, where it's relatively fast. So this isn't to say that for loops in R are bad, it's just that for loops in other languages are better. If we can extract that into the other language and do that easily, then we definitely should. It takes a little bit of time to get used to using and writing functions in this vectorized manner. So for example, when using the rnorm function to generate normal random variates, we can set our mean and standard deviation to be vector values. But one thing that we need to be careful of here is that if we had this as being 1 through 100 and rep1 100, then we'd have each individual random variate having a monotonically increasing mean. But when the argument lengths don't match precisely, R recycles those vectors. So here we'll get a rolling sequence with means increasing from 1 to 10 and then back down to 1 10 times over. Feel free to investigate this a bit further and make some plots to really get comfortable with this idea, because this is something that you need to be aware of, both when you're using other functions and when you're writing your own. As a special case of working with vectors, if you can write any R code as a linear algebra expression, I would highly recommend that you do so, because again, these inbuilt operators are designed to be incredibly efficient. If you can represent something as a series of matrix or vector operations, then that is going to be much faster than using a loop-based approach. If you'd like to see some more about how you can write this sort of vectorized code, then I'd highly recommend you check out this blog post that I've linked to by Noam Ross. So one thing that people often really get excited about when writing code is turning their loops into a more functional programming equivalent. And in base R, the way that you do this is by applying a function over a list-like object. And here we have several variants of the apply function depending on exactly what your inputs and outputs are. To see an example of this, we can make a matrix A that just has the numbers 1 through 12 stored in it. We can then apply the sum function over each row to get a vector of row sums. If we want the column sums instead here, we can just switch the margin that we're working over to 2. And if we're working with a higher dimensional array rather than a two-dimensional matrix, then we might want to take that margin over the third or the fourth dimension of that higher dimensional array. What this apply family of functions do is generalize a set of functions from the matrix stats package, which use compiled C code to calculate these sorts of summaries over list-like objects incredibly efficiently. So if you are wanting to specifically calculate the sum here, there's a pre-built version of this function called row sums that extracts all of this looping out into a highly efficient function. It gets you the same result, but it gets you there faster. One thing to note here is that the apply function isn't doing anything more or different to what looping over the 3 rows of this matrix would be doing. The row sums function is doing something fundamentally different because that loop is no longer in R. Another disguise that for loops sometimes wear is the map function from per. The per package provides lots of functions for iterating over list-like objects, each with a slightly different naming convention depending on the form of the input and the form of the output. The most basic of these is the map function, which takes a single first argument that's called .x and a function .f that we want to apply to it, as well as any additional arguments that we're passing to that function. So in the left-hand example, we can see that we're generating 3 sets of normal random variates, each of length 5, where the first set has a mean of -10, the second set has a mean of 0, and the third set has a mean of +10. Within the per package, there are also functions to iterate over multiple objects. So if you have 2 inputs, there's the map2 function, or if you have more inputs than that, there's the generic pmap function that can iterate over any number of parameters. In this case, we've modified our example slightly, so we have our first input being the mean, and the second input being the standard deviation that we're feeding into this rnorm function. Again, in the same way that the apply functions take a little bit of time to get used to, so do these per functions. And if you'd like to see some excellent worked examples of those, I'd highly recommend you read through chapters 9 to 11 of Advanced R, which are dedicated to this style of functional programming. But again, this isn't doing anything better than a for loop, it's just a different style of presenting the same approach. One way that we can speed up this looping procedure and make it more efficient when we're starting to operate at scale is to run those loops in parallel if they don't need to be run in sequence. So an example here might be running a simulation study where you have lots of different parameters that you want to run, but there's no real dependence between the order that you run them in. There's 2 packages that are really good for letting you do this, the first called Parallel and the second called Futures. These are really, really powerful tools, but they've got quite a steep learning curve associated with them as well. So there's been a wrapper package that combines the functionality of the Futures parallel coding package with the per package for functional programming. This means that there are parallel analogues of all of the per verbs where you just have to add a prefix of future underscore to them. So here we can see that first example recreated where we're generating 3 sets of normal random variates. What we need to be really careful of when we're doing this sort of parallelization is handling random numbers correctly. Thankfully, the fir package will now warn you of this automatically, and this is why I've got this extra line where we're setting the seed option to be true, so that we're using consistent seeding across these generations. you'll notice that we don't get the same set of random numbers out. This is done in such a way that the seed carries on after the end of the first run onto the second, onto the third. If you'd like to learn more about how to carefully handle seeds during this sort of parallelization, then there's an excellent blog post on the R-bloggers website that you can take a look at. The final way we can think about improving our code before putting it into production is to write it in a different language. Sometimes R just isn't the right tool for the job. It might be the case that you've got lots of loops that need to be run specifically in order, so you have a sequential logic to a really expensive loop that you need to run. It might also be that you have deep recursion within your code, so you have a function that calls itself many times. And the classic example of this is when calculating factorials. If you're trying to calculate a large factorial, you have to repeatedly multiply by the previous factorial result. But that sort of construct pops up all over the place in programming, and so getting these nested recursive functions can be a good motivation to move to a different programming language where calling a function has a smaller overhead. So if you're calling a function many millions of times, you can have quite a dramatic impact on the overall performance of your code. The final thing that you might want to consider when using a different programming language is that different languages have different data structures in them, which are better at different things. There are some data structures that are available within C++ that are faster or more efficient in terms of storage and lookup than the R equivalents are, and so converting your R code into C code to exploit these data structures could be another source of efficiency before putting your code into production. This idea of linking R to C++ does take quite a long time to get used to, because you're having to familiarize yourself with two different programming languages and how they interface together. I bring it up now because it's important to know that this exists, so that you have the option to learn that and use that in the future. So let's wrap up this video here then. As a summary of what we've discussed, it's really important to pick your battles wisely. You need to select where you're going to optimize your code based on the specific production context that it's going to be implemented in. Otherwise, you could spend a lot of time making performance gains that relatively are very large within that small part of your project, but as a part of your project as a whole are actually very small. You then need to target that energy that you're putting into improving your code very specifically at those areas that you've identified as having the largest benefits for the smallest effort. This might be improving the speed of your code by changing from a loop style structure to a vectorized function, or it might be that your individual iterations within your loop could be run in parallel across many cores on your computer, cutting that down to a fraction of the time. This gets particularly powerful when you link it with remote computing, where you can set up very many cores running at once. And our final and very last approach should be to scale our code by working in another language that is more suited to the task at hand than R is. Here we have to note that what we're doing is actually more effort than translating our code, because not only do we have to get it working in the other language, we have to get it interfacing with R as well. However, this is a really powerful tool that lots of R packages use to provide the functionality of these other low-level languages to R users. These ideas of code profiling and code optimization are really quite complex, and there could be an entire course dedicated just to this. If you'd like to get started looking deeper into this, I'd recommend any of the articles and blog links that I've mentioned throughout this talk. The R Inferno book, which details different ways that R can go wrong, particularly the chapters relating to circles 2 to 4. The 7th chapter of Efficient R deals with similar topics, while the final chapters of Advanced R deal with this sort of code profiling and rewriting in other languages. Thank you very much for your attention, and I'll see you in the next video.